Welcome, everyone. Welcome, everyone. We are very privileged and happy to welcome today Robert Rosner from the University of Chicago, who agreed to give a lecture today in honor of Gene Parker, who sadly passed away in March this year. And Bob was ready to fly to give this lecture here, but it's a very long flight for just a very short visit to give the lecture. So we decided it's probably better to do it via Zoom. So thank you very much, Bob, for this occasion. And if you want to ask questions, it's better that we use the microphone so that Bob can hear us. So the best maybe is to leave wait for the end of the talk before we ask questions. Bob.
Well, thank you very much. Just to start, I don't mind being interrupted by questions, but it may be a little bit awkward, but I don't really mind. So let me just start by saying that I'm really there's a mixture of regret and pleasure about talking about Gene. Regret, of course, because he's no longer with us, but pleasure because I really enjoyed working in the same place that he spent so much time at, most of his life, actually. And he was really a great colleague to me. And what I intend to do is to basically talk a bit about him, his science, and then also to spend a little bit of time talking about him as an individual, as a person. So what struck me about Gene Parker was that he had a kind of a unique approach to doing his science. Of course, he started out as a physicist. He was not an astronomer to begin with. He got his PhD at Caltech in physics, and the way he came into contact with astronomy was in his first job. He was hired at the University of Utah by Elsasser, who of course at the time was awfully interested in the geodynamo. And that was Gene's first contact with astronomical sciences. And I'll talk a little bit more about that particular aspect later on. There's something about Gene, the person, that makes him, that I think influenced the way he did his science, which is he was also a sculptor, carver of wood. His house was always replete with carvings that he had done, really beautiful things that he created. And he also built his own log cabin. So he was a very practical sort. And I imagine that if he hadn't gone to Caltech and become a scientist, I could see him having become a mechanic. So he really thought about things from the perspective of how does this thing work? And I think that approach of starting with trying to answer the question how something works before you engage with engaging the machinery of mathematics, I think characterized much of his work, his career. So he really thought of the sun as a kind of a tool for exploring astrophysics problems that nature had given us a gift. The gift was the sun placed near us. And by looking at the sun carefully and studying it, one might be able to shed light on all sorts of things about stars that we wouldn't be able to deal with in any other way. And it's kind of perhaps both ironic and interesting that the one mission that NASA launched that was named after a living person was the very mission that basically is accomplishing exactly what Gene had always wanted to do, which is literally to touch the sun. That is to literally be able to do in situ measurements of the plasma that the sun is made of, and not only count on remote diagnostics. I'll get back to that a bit later on as well. And as I already mentioned, his style was really first trying to figure out how something worked, and then using his mathematical talents to do the actual physics. I'll also say that he was kind of an originalist. He tended not to work on problems that other people defined. He liked to strike out on his own, often in ways that were unique, and he did this repeatedly. Now, I'll give some examples in a moment. So his interests are also quite broad. I just made a list of the kinds of problems that Jean worked on. This is kind of a semi-chronological list, starting with the very first paper that was published as a paper in astronomy, astrophysics, in his dynamo paper, 1955. Just to provide a little context, after the University of Utah, where Jean was an assistant professor, he came to the University of Chicago. He was hired by John Simpson, and John was was of the generation of folks at Chicago, physicists at Chicago that worked on the Manhattan Project. He was a major figure in the U.S. Interplanetary physics community. He was responsible for launching an enormous number of satellites to explore both the interplanetary medium and the Earth's magnetosphere. And he led a group that was also co-led by Peter Meyer, another main figure in this field. And they needed a theorist. Both Meyer and Simpson were experimentalists. They needed a theorist. And for reasons that I can't explain, they identified Jean as the person who'd help them out. So leaving Utah, he came to Chicago and began to interact with the Simpson-Meyer group. And many of the papers that were written in the 50s were motivated by issues that were discussed at the time by Simpson and Meyer. And I'll talk a little bit more about that in a moment. So you can see the breadth. I have at the bottom here, I have a ... because this is not the exhaustive list, but it's certainly it's the things that I'm most familiar with, things that he's worked on. So the two topics I'm going to concentrate on are, for obvious reasons, his work on dynamos pertains a bit to the topic of your meeting at the Newton Institute, and then, of course, the famous paper on the solar wind. So to begin with, it might be useful just to point out that there's some unique things about the way Jean did his work. First of all, if you ask what fraction of his papers were multi-authored, the answer is a very, very small fraction. Most of his papers, by far, were single-author papers. He insisted that his students' research was always to be published as single-author papers. He never, ever put his name on papers that referenced the thesis work of his students, ever. And you can count the number of papers that he's co-authored with other people. I think I think 5 is a pretty good number. It's of order 5 out of hundreds of papers. He was a prodigious worker. In most years, you'll find 5+ papers, single author papers written by Jean. I remember how he worked. It was kind of interesting. When he was in his office, he just focused on work. When he went home, he completely devoted his time to his family. I was told by his son, Eric, that he never brought work home, ever. He commuted. He lived in the suburbs of Chicago. He didn't drive. He came in by train. And he told me the reason he did that because he could start working as soon as he got on the train, continued arriving in Chicago, working in his office, then back on the train, working until he got off the train at Flossmoor, which is the suburb he lived in, and then he stopped. So he was very compartmentalized in how he lived his life. He's also kind of a classic a classic theorist. That picture there is a picture of his main computational tool, the slide rule. I never saw Gene ever use a calculator of any sort. He most certainly never did numerical simulations. I highly doubt whether he knew how to program. I'm dubious about that. I'm not certain, but I have a suspicion that he actually didn't know how to program. He wasn't interested in it. He was an accomplished applied mathematician of the classical type. And as I said earlier, he was just a highly intuitive worker. He really focused on how things worked. And he really knew how to translate ideas about how something worked into mathematical language. He was really expert in that. So let me start with the solar wind. Of course, the history goes back, solar wind goes back to actually Eddington, who apparently, he certainly didn't have a theory about the solar wind, but he apparently did notice that something like a solar wind must exist. And the evidence that we have for that is that there's a footnote that he has in a paper of his in 1910, where he mentions that the sun might have a solar wind. And Birkeland was the first one to actually identify the composition of what might be the solar wind back in 1916, because he was motivated by studies of aurorae and realizing that it's likely that impact of something from outside the magnetosphere is likely the cause of aurorae. The first really serious work on the outer envelope of the sun was probably done by Sidney Chapman and Ludwig Biermann, but they had very different perspectives. Chapman was interested in heat transport outward from the very hot solar corona, and his view was that the outer atmosphere of the sun is perfectly static. And Biermann realized that that idea was flawed, and he came at that by thinking about the plasma properties of this multi-million degree gas. Namely that if you think about the distribution function of the electrons and protons in this gas, it was clear that the tails of these distribution functions had particles in them, protons and electrons, that certainly had speeds that were well in excess of the escape speed from the sun. And so they must be flowing outward, especially given the fact that the density, we knew that the density was dropping substantially, and therefore the mean free path was large. So Biermann certainly didn't subscribe to a static corona, and in particular, he thought about this in the context of how the sun might be affecting cometary tails. Now, the fact is that at the time, these are early days for plasma science. And so the kinds of calculations that Biermann, for example, had done were limited. And the estimates, for example, that Biermann had of both the plasma density and the plasma velocity at 1 AU were way off. And it's not surprising. I mean, this was really early days of doing these calculations. I should say, just in anticipation of any question, that of course today we certainly know how to reconcile the hydrodynamic description of the interplanetary medium with a particle description or kinetic description. It's no longer an issue. Now it turns out that Biermann had visited Chicago, in particular John Simpson's group, in the mid-1950s. And he presented his ideas about what must be going on to that research group. But John Simpson in particular was very dubious. He just couldn't believe that stuff was flowing out of the sun. Found it difficult to believe. So Gene was the kid on the block, and he was hired as the local theorist. And John said to him, John, by the way, was a definitely type A personality. He was a very dominating type. So I can just see that that interchange. John said to Gene, more or less, go figure out why Bierman is wrong. And Gene took up the challenge. And his starting point was not to follow Bierman's approach at all, but to use the hydrodynamic approach. And of course, that's what that 1955 paper is all about. And of course, the puzzle is something that Gene absolutely must have known, which is that if you think about the mean free path of protons, electrons, for example, at 1 AU, that is of order 1 AU. In other words, what we're talking about is a collisionless plasma. And it's hard to see how hydrodynamic description at the time would be appropriate for modeling a collisionless plasma. But nevertheless, Gene proceeded and basically came to the conclusion, this is, of course, the famous result, that yes, indeed, there is a solar wind. In fact, it's inescapable. And Bierman was correct. Maybe not correct about the details of the plasma properties, wind properties, but he was correct that there must be an outflow. There must be an outflow. So it turns out, of course, what I always found kind of surprising, interesting, was that in the paper itself, there's never a mention of this issue that we're using hydrodynamics to describe something that is not collisional, not discussed. And as far as I know, Gene never really addressed that problem. It was addressed, of course, much later by the interplanetary science community, but he didn't address it. So in some sense, it wasn't surprising that when his paper was submitted, it was really heavily criticized by the referees, and who all the referees urged that the paper be rejected. But it turns out the editor of the Astrophysical Journal at the time was Chandrasekhar, whose office was just down the hall from Gene. And Chandra then took it upon himself to read the paper. And from the point of view of just the mathematics, he thought, well, it's correct. I don't see what's wrong. Of course, it seems crazy. Yes, Chandra did realize that there's a little bit of a problem in describing a collisionless plasma with using hydrodynamic equations, but okay, let it be published. So it was published in 1958. Amazing. So if you now ask, what did Gene get right? Well, he got right the fact that the wind was supersonic. And from what we today call the slow solar wind, he basically nailed its velocity of the order 300 kilometers per second. And he basically got the densities right at 1 AU. And that, of course, was all validated by satellites that are the early satellites launched by the Soviet Union and the US in the late 50s. Lo and behold, the solar wind was discovered, was measured. Of course, later work then revealed that the solar wind isn't quite so simple. There are also high-speed streams. They go at speeds more than twice the slow wind. And if you ask whether they're thermal thermally driven wind could possibly account for these high-speed streams? The answer is no. You'd need temperatures that basically were just implausible. And so the obvious question is there another mechanism for driving it? And I think even early on, it was pretty clear that to answer that question, you needed in situ measurements. The people like Simpson and Meyer, of course, had pioneered the idea of using in situ measurements for exploring the interplanetary medium. But the driving part, of course, well, that was at the sun, within a few solar radii of the surface of the sun. And you need to get there in order to really establish what was actually driving the high-speed streams, and in general, also heating the solar corona. So the idea of doing these measurements close by the sun basically dated back into the 1970s. And I remember as a young postdoc and junior faculty member, discussions about how you might do this. I remember the people joked about building a solar plunger, but lo and behold, just 3 years ago, NASA finally launched the renamed solar plunger, the Parker Solar Probe. That's doing exactly what Gene actually really wanted. So I have a picture down on the bottom of the solar probe with its heat shield, and next to it on the right is a description of the orbits, starting from launch and using Venus to basically alter the orbits so that you get a highly elliptical path where the point of closest approach moves closer and closer in to the surface of the sun as the spacecraft ages. So this is really an amazing thing that Gene really motivated, and rightly was his name was used to name this spacecraft. And I would also say it was just really great that he actually witnessed the launch of this mission. He went down to Cape Canaveral to see it, and I think that was just fantastic. So the second topic I wanted to talk about is the solar dynamo. So of course, this is a topic that all of you are pretty familiar with, and I'm just not going to go into the details of the history, except to just say that Cowling's anti-dynamo paper, of course, was just an incredible inducement for many theorists to try to figure out how to get around that theorem. And I would say that through the 1950s, most of the successful efforts of getting around the theorem involved flows that were, I would say, physically implausible if you thought about using those flows to model what the sun was doing. Now, how Gene got into this business was, as I mentioned before, from Caltech, he moved to the University of Utah, where Elsasser was. Elsa was working on the geodynamo. There are these papers, in fact, by Backus and Elsasser about how the geodynamo was working, and Gene, of course, was there at the time. And when he went to Chicago, his thoughts turned to thinking about these ideas in the context of the sun. So as I said before, he really started always with the perspective of how might something really work before you actually write down any equations. And so he focused on the fact that the sun was most likely differentially rotated in radius, and that if you thought about rising bubbles, magnetized bubbles in the interior of the sun, that they would probably experience Coriolis force. So twisting of these bubbles, and therefore twisting magnetic fields if these bubbles contain magnetic fields. And lo and behold, there's the equation that he derived. And in the 55 paper, and I've written it in the way that he wrote it out. So what subsequently became called the alpha effect in that original 55 paper was the gamma effect. Same thing, of course. And what I found so really striking was that this equation was written down entirely based on his intuition of how he thought the dynamo would work, and that a rigorous derivation of this equation, starting with the induction equation in Navier-Stokes, Euler, didn't really occur until almost a decade later, when both Brzezinski and the East German physicists Steenbeck, Krause, and Radler basically used mean field theory to formally derive the very same equation. Of course, the advantage of doing the formal derivation is that you also see what the limitations are. It's not so easy to see that from an equation that you write down basically based just on the intuition of how something might work. Now, I want to turn a bit now to a slightly different topic, which is Jean's interaction with the solar community. So the solar plunger notion that I talked about before is really just one of many examples of how Jean inserted himself into this science politics of astronomy in the United States. He was not shy about stating his opinions about what NASA and the National Science Foundation should be doing. And in fact, he, because of his prominence, he chaired a number of National Academy meetings. I think most of you are familiar with the fact that in the US, there's a regular process by which the National Academies issue decadal reports, including for all sorts of fields, including astronomy and astrophysics. And Jean was always, in the early days, an active participant in these deliberations. And just to give you a particular example, in the early 80s, it was pretty clear that that to make much progress in trying to understand what Jean called fibril magnetic fields on the surface of the sun would require instrumentation that was a bit better than the 1 meter class solar telescopes that were then in existence. So there's a lot of effort on both sides of the Atlantic put into this. Some of you who were around then will remember the Advanced Solar Telescope that was brooded about, 2 meter class telescope. But basically, nothing was actually done. I think the funders were not particularly enthusiastic. And it wasn't until around 2012, 2013, that the National Science Foundation of the United States finally decided to proceed. I should say that this was done because there was actually an understanding on both sides of the Atlantic that it was time to proceed. So this new telescope, which is now called the Daniel Inouye Solar Telescope, DKIST, was started, I think construction started in 2013. And it turns out it was dedicated just this past August, just a couple of months ago. But first light actually happened in 2019. I'll show you some results in a moment. This is a telescope in which Europeans, in fact, are participating both in terms of funding, in particular on the instrumentation side, as well as on the observations. So it's really a nice example of the solar community really being an international community. The other thing, I can't resist also pointing out that the National Science Foundation does things differently than NASA. NASA tends to name its telescopes after prominent scientists. NSF sometimes does it, but not usually. Usually it names things after prominent funders. And Daniel K. Inouye was the senior senator from Hawaii that had made it his business to see that this telescope got built. So he got his name onto this telescope. So here is one of the very first images of the surface of the sun taken by this telescope. There's a lower left, you can see the United States. So that you can get a sense of the scale of what we're looking at. And this is an amazing picture. It's just so much better than what could be done until this telescope was built. This telescope has the amazing characteristic that it can actually reach the diffraction limit of a 4-meter class telescope looking at the sun, which is remarkable because it means that one had to invent adaptive optics that could work on the sun, where you can't use things like laser guide stars. So it's really an amazing technical achievement to be able to reach the diffraction limit looking at the sun, a 4-meter class telescope. It's an incredible, really incredible image. And of course, I can't resist for dynamo theorists, especially fast dynamo theorists, to show a movie. And this is just the movie. I hope this is playing in Cambridge of solar convection. And of course, what you're seeing there is these white places are, of course, the places where flux tubes are being gathered and being formed by this convection band. It's really fantastic. Okay, so the last thing I want to do is talk a little bit about Gene Parker, the individual, the person. So I first met him in 1980 in the other Cambridge, and it was kind of for me, I was a junior faculty member. It was kind of a scary moment for me. So I was meeting this great personage, and I thought it was okay. He was a very personable individual, and in fact, he was singularly involved in convincing me to leave Harvard to come to Chicago. He had a lot of advice for me on the science part, but also on administrative matters. Just to give you a sense of the guy, two things that he told me when I was elected chair of the astronomy department, it was in 91, 92. He said, Bob, make sure that you don't spend a lot of time in the chair's office, because the staff there is really good at figuring out what you should be doing. And they are sure to make sure that your time is entirely occupied by doing administrative stuff. Don't spend time in the office. The second piece of advice was that that if you do department business, one good way of dealing with it is as you're walking from the chair's office back to your own office, that's when you should do the department business. I actually paid a lot of attention to this advice. And I can tell you that the administrative staff was not happy about that. But Gene was right. I think he was right. Yeah, I think he also, yes, those of you who know Gene, that he wasn't really all that interested in idle chatter about this, that, and the other thing, especially academic politics. He really had an intense dislike about just the politics. But he did take administrative matters very seriously. One thing that that you may not be aware of is that he was appointed chair of the astronomy department in Chicago, even though he was not a member of the astronomy department at the time of his appointment. He was actually, his original appointment in Chicago was in the physics department. And you might ask, why was that? And the reason is that because the astronomy department had fallen on really very difficult times in the 1970s. It was beset by all sorts of conflicts between different faculty members, to the point where Chandra, who was actually in the astronomy department, decided to actually, and actually had lived up at Yerkes Observatory in Wisconsin, decided to quit the astronomy department and move to the physics department and move to Chicago. So the astronomy department was really in pretty bad shape. So the dean of physical sciences took it upon himself to ask Gene to take the department over, and gave Gene the ability to make appointments without worrying too much about what the rest of the faculty might think. And Gene basically rescued the department. His first appointment was David Schramm. He really had an amazing eye for talent, for smart people, and he brought them in. So I would say that he was a sage person, clear thinking, very pithy, always to the point. But if you really wanted to get him engaged in a conversation, what you would do is you'd approach him about some science book. He loved talking about science. It didn't really matter whether it was a topic that he himself had been working on or something else. It didn't matter. If it was science, you could engage him. Otherwise, yeah, not interested. So just to end this, I think you can guess that I really missed the guy. He really was, what I say here is really how I think about it. He was a gem of a person. So just an incredibly good, great individual and a gem of a scientist. And it was tough to lose. It was. So with that, I think I'm ready for questions.
Thank you very much, Doug. Questions, comments? Yes, please. Microphone.
Bob, that was wonderful. Thank you very much. One question that occurred to me, you mentioned Chandrasekhar, just one point. How did Chandrasekhar and Gene get on together, as it were, over the decades that they were there in Chicago?
So I think they were friends. I think the intersection between Gene's science and Chandra's science was relatively small, and in terms of topics, and certainly in terms of time. As all of you know, Chandra did have a period when he was interested in hydrodynamics and MHD. And of course, whenever Chandra focused on a topic, there was always a monograph that came out. So of course, that monograph was published. I think all of you are probably aware of it. But once Chandra moved on to another topic, he really wasn't all that interested in other topics. I should tell you that one of the most fearsome experiences I had was when I was asked to come to Chicago for my job talk. You know, you have to perform, right? So I showed up, and Roger Hildebrand, who was a physicist, then a then chair of the physics department, said to me so something like 10 minutes before I started my child, he said to me, Bob, Chandra will be in the audience, but he has a habit that if he finds the topic not of particular interest to him, that he will just get up and walk out. So you can imagine that I spent the entire time of my talk glancing furtively in the direction of Chandra to see whether he would actually leave. Lucky me, he didn't. Maybe I reminded him of some of the work that he had done in the 60s. But Chandra was very reserved, and but I think he appreciated Jean's singular focus. And what I said earlier, the fact that Jean liked to talk about science, I think that really struck Chandra as, yes, this is a person I could get along with. So I think the answer, the direct answer to your question is I think they got along very well.
Hi, Bob. How are you doing?
Hi.
Good to see you. I was always very struck with Parker's papers because he would adopt simple models which could be solved in terms of, Bessel functions or whatever. And,
Yes.
and the numbers carried through to the third decimal place, even though it was totally irrelevant to the answer. And do you have any explanation for this? I always find it very peculiar.
Yes, well, I showed I showed his computational device for a reason.
Yeah.
Okay, you can't get 3 decimal. It's tough to get 3 decimal places with a slide rule. Okay.
Yeah.
One of the you might ask. Here's a question you could have asked, which is, Bob, in all of Gene's papers, there are always these graphs.
Oh, yeah.
And surely he must have done computations to construct the graphs. And the answer is no. The graphs were not done by him. The graphs were done by a woman who was amazingly good at computational mathematics.
Oh.
And she's the one who did it. Yeah. Her name was Donna Elbert.
Oh,
I should tell you that Donna Elbert also worked with Chandra. Many of Chandra's papers, the graphs, were also constructed by Donna Elbert. And in very belated recognition of Donna Elbert's talents, the astronomy department is just putting a plaque up in our building in her honor. This woman was completely and totally unappreciated by the faculty, and it is really it was a sign of the times. I must say it's kind of tragic. This woman was fantastic, and she did all the calculations.
But the graphs were hand drawn.
The graphs, yes, all that stuff was done by Donna Elbert. Right.
Thank you.
Yeah.
Any other questions? Comment maybe online if you're following the seminar via Zoom, and if you have a question, you can turn your microphone on. We have another question from Keith.
You commented that it was about a decade between Parker's great 1955 paper on dynamo and the work of Roginski and the East
Right.
German group.
Right.
Why do you think it was that there was this long delay and very little, I don't know, response somehow to the paper of Parker over that long period?
Yeah. It's a really interesting question. I think I think what what the delay is related to is the evolution of development of mean field theory within the plasma community, which took place in the 60s, I think. And certainly Brzezinski was right in that domain. And if I remember correctly, the Germans had actually spent, they were really very heavily involved with the Russian theoretical physics community, right? Because I think all three of them had actually spent the war in Moscow. They were so in the sense that there was this community of physicists who were developing the weakly nonlinear theory basis for plasma science during that period. And if I remember correctly, I think all three of Rayleigh, Krause, and Steinbeck, I think they were originally physicists. I don't think they were astronomers. So I think what we're seeing is just that delay just reflects the development of that field. I think in 1958, I don't think anybody was prepared to do the analysis that finally was done. By the way, one thing that is kind of sad is that the German work was really not appreciated in the West until I think Stix and Roberts, yes, right. Roberts and Stix had read the papers because I think they had visited in the early 60s Potsdam, the Sternwarte in Potsdam, and gotten to know those folks and realized that they had published stuff that never was noticed in the West. And I believe they basically published the translation of the East German work. That's how it came to notice. And I think that was done late. I think that was published maybe 71. Maybe somebody then remembers, but it's not, that's my memory. It was actually published of the order 3 years later after the work was actually published in German.
So I know it's really early days, Bob, but what would your pick be for the kind of most interesting results to come out of Parker Solar Probe or DKIST so far?
I think the solar probe results of these slingshot events. I mean, it turns out that the much of the dynamics of what we see at 1AU is really driven by reconnection events, complicated dynamics that happen within 3, 4, 5 solar radii of the sun, surface of the sun. And so I think we're going to get a very different picture of exactly what drives the wind in the first place. Then in particular, I think we have a shot at answering the question, what exactly is heating the solar corona? Is it these what Jean called these nanoflares or not? Is it really this cascade of very small scale reconnections that's doing it, sort of an avalanche effect? So I think that's it. And what's so interesting, and should be kind of maybe a caution to astrophysicists, that the only way you ever will know what actually goes on is unfortunately to do in situ measurements. That trying to figure out how these things work using remote diagnostics is probably impossible.
Thank you. So you mentioned the work by Backus and Herzenberg on the early, very mathematical constructs for dynamos.
Right.
And Backus was in Chicago at that time, I believe. Did they have a warm relationship?
The answer to that question is I don't know. I think Backus, I suspect that they actually met earlier because I believe Backus had worked with Elsasser, if I remember correctly. And I suspect that's how Gene probably, I think that's where they'd actually first, engaged. And your question is, I wish, I wish I had thought of asking Gene that question, but I don't know the answer.
I guess I'll just have to ask George.
Yeah, it's a great question.
Any other questions or comments from the room or on Zoom?
Well, comment on that. The difference was that Backus and Herzenberg both provided a fairly rigorous argument and established beyond doubt that dynamo action was possible in a homogeneous fluid medium. And so in a way that was quite different from Gene Parker's approach, who,
Yes.
as Bob has emphasized, was relying on deep physical intuition and coming up with wonderful ideas at that time, which I think it has to be admitted were on rather shaky mathematical foundation. And that is why Cowling, in his Interscience text in 1957 or 58, was very dubious about the Parker theory. And he said, well, there's maybe some good ideas here, but more work is needed, sort of thing.
Yes. Yep. Yeah. It's interesting that Gene really spent no time at all worrying about a formal derivation of that equation. He just wasn't interested. So quite different. I think what you said is absolutely right. He simply was not interested in doing the kind of work that was done by people like Backus and so on. Yeah. Right.
Any more? Not online? Not that. Thanks, Bob, again. Thank you very much.
It's a pleasure.
Thank you very much. Goodbye.
Take care. Bye-bye then.
Bye-bye.